Welcome back, everyone. It's my pleasure to reintroduce you to Raymond Lal, who's going to give us a talk on public capitalism and principle of common cause.
Right, so this is joint work with Eric Cavalcanti. Unfortunately, he couldn't be here. That's him frolicking on the beach. So basically, I want to explain a couple of things. Firstly, I want to explain the relationship between Bell inequalities and principle of common cause, which arose earlier today as a question. And I will briefly discuss a generalization of the classical notion of common causes, which I think is problematic, and I'll explain why it's problematic. So what's the context of this? So actually we can state the principle of common cause by a very simple example. Supposing we're told that some rare viral infection spreads simultaneously in Australia and Brazil, what would an epidemiologist think of as some explanation of what's going on? Well, they probably have three possible explanations. Firstly, someone from Brazil travelled to Australia, carried the virus with them. Secondly, Brazil to Australia, or secondly, someone travelled from Australia to Brazil. Or thirdly, someone travelled to both of these places and spread it from some third country. So, Reichenbach's principle of common cause just stating formally this simple intuition about observing correlations, either one or the other, or there's some third cause of them both. So here's some sort of more conceptual context about the principle of common cause. And it's in a sense surprising that it was stated quite recently, some 50, 60 years ago. It took some reflection by Hans Reichenbach, who was a philosopher of science who was interested in various issues that are actually of much relevance to people considering quantum foundations. So firstly, the meaning of probability, whether it's frequentist or Bayesian interpretation. Secondly, the interpretation of space-time and causal structure in relativity. And he was also very interested in quantum theory and came very close actually to stating Bell inequality, in words stating the fact that quantum theory violates some kind of notion of causality that we would expect to be satisfied classically for this causal anomalies, but he never really wrote it down formally, and so didn't get credit for it, which is fair enough. And so what I'm talking about here is at the intersection of these three areas. So in a sense, the principle of common cause it concerns the interaction of probability and betting these probabilities in space-time, and quantum theory presents itself in the guise of Bell inequality violation. And so Reichenbach stated this principle for the first time in 1956 in a book concerning the direction of time, actually. He wanted to show that the direction of time can be explained by the direction of causation, and that's why he was thinking about ideas of common cause and also these colliders, these common effects that I briefly described in my earlier talk. So let's state it more formally. So we can actually decompose it into three different principles. First one is stating that there's a trichotomy that we're presented with when we observe correlations between two random variables, A and B. A and B are not dependent here. And as I was saying, we must either explain those correlations by A causing B causing A, or A and B sharing some common cause that explains the correlations. But we have to state what we mean by certain terms in this statement. So in particular, we need to explain what we mean by common cause, and we also need to explain what we mean by an explanation of the correlations. And we can state that as follows. So what we shall mean by a common cause is some event, some random variable lambda in the common path of A and B, which leads to this factorization. So earlier actually for this, the Markov condition for the fourth DAG. And another way of saying this is that lambda screens off the correlations between A and B. Once we know lambda, A and B are independent. So that's what we mean by a common cause. And what do we mean by an explanation of the correlations? Well, we mean that when we include lambda in our distribution, but we sum over lambda, which we're ignorant of because it's introduced by hypothesis in order to recover the correlations, that we do indeed recover them. We can decompose this probability distribution as a sum over lambda. And in fact, with just that piece of structure, we can very quickly get to Bell's theorem. We just need to impose a fourth property, which is the causal structure of, say, Minkowski spacetime, in which we're assuming that Alice and Bob cannot communicate to one another. And so when we're presented with those three choices, we cannot accept either the first two, that A causes B or B causes A. So we must posit that there's some common cause. We have to take the third prong of that triposit. And indeed, it's very straightforward to show that we obtain exactly Bell's locality condition by assuming these four assumptions. And diagrammatically, this is what it would look like. Alice and Bob have independent processes, but they're sort of controlled by this shared randomness that they have access to. So this way of stating Bell's theorem, I think, is different and insightful because it allows us to classify different ways of responding to Bell's theorem. So typically people want to say, well, okay, quantum theory is not local, but it still keeps some notion of locality, or in our case, a notion of common cause. And so here in the columns we can write down the different assumptions that we use in order to get to the locality condition, and we can think of different approaches that people take in response. So I'm going to discuss this non-commutative example, but let me just briefly mention some of the others. So for example, Van Fraassen in the 80s responded to Bell's theorem by basically saying, well, I don't care about this idea of principal common cause. I'm going to deny that we need to state this trichotomy at all. And a different response is Bohmian mechanics, which denies that relativistic causal structure is something we should assume. There just is, in that theory, there just is a non-local action that breaks the space-like separation between A and B. So the question is, do any of these approaches recover something that looks like a plausible generalization of the principle of common cause? So let me discuss this non-commutative version. It's actually, so this has been developed for some time. I think over a period of 20 years, various iterations of it have occurred. And usually in the framework of algebraic quantum field theory, and it's a group of Hungarian researchers that have been working on it. And so what is it saying? So simply, basically, it's saying that we have this some device producing these correlations, and we get some Bell inequality violations. We know that we cannot posit some hidden variable lambda in the joint paths of Alice and Bob. And so instead, they're going to assume that, or try to explain these correlations by saying that there's some sort of quantum-like property there that is what is explaining the correlation. And so I'm not going to explain it in the formulas of algebraic quantum field theory, and I don't think that's particularly necessary. The reason why it was done so is because people in that field are very concerned with defining isolated regions of quantum mechanics and assigning operators to different regions. And so if you state it in ordinary quantum mechanics, it's not necessarily dealing with localized operators. But in any case, we discuss Bell inequalities in the usual formalism of quantum mechanics. So we may discuss these in the usual formalism of quantum mechanics. And their definition, a simplified version, basically saying that we're given some bipartite state rho and some observables Alice and Bob. They say that there is a common cause, a non-commutative common cause, given by this collection of projectors corresponding to a measurement C, if this equation holds. So what does this equation correspond to? It looks structurally like a factorization, but a sort of quantum version in which
Is that a solution or
projected, yes. And what it corresponds to, using the Luder's rule, is actually indeed factorization of probability. It corresponds to the fact that conditioned upon one of the outcomes, CK, in this collection of projectors, we have the factorization of probabilities equation. So in other words, if we were to perform one of these this measurement C, then we would get the associated factorization. So that's fine, but actually it's straightforward to show that the law of total probability fails, meaning that you cannot sum over the probability of getting each of these CKs and still recover correlation. So the problem really arises as follows. We have, it's easy to show that actually any orthonormal basis for this measurement C can provide a common core system when that is the basis of product state. And it will do so for the correlations of any quantum state. So there's a kind of double degeneracy here. So given any quantum state, we can provide a non-commutative common cause using any basis of product state. And the significance of this is that there's no deductive link between the non-commutative common causes and the observed correlations. Precisely because although factorization of probabilities is satisfied, we get this nice Markovian rule, they only have meaning in a counterfactual sense, because this non-commutative common cause is not actually measured. If it were measured, then it would just collapse this initial state rho to some product state, and we wouldn't get Bell inequality violation. So they have a very strange sort of meaning, because it provides a formal analog of a normal common cause, but actually when you sort of drill into the details of how that occurs, they don't really provide an explanation of the observed correlation. It's just a counterfactual situation in which you had measured this observable C. So let me just summarize what I've said. Reichenbach principle is arguably one of the most fundamental principles across a range of different sciences. Bell's theorem clearly challenges this. As I've explained, we can derive Bell's theorem by using the principle of common cause. But the generalizations of the principle of common cause seem quite difficult. And hopefully what I've been talking about is useful because it allows us to classify different responses according to the different ways in which the common cause principle will fail. So I'll stop there.
Anyone has any questions?
So maybe this is a definition of the factor non-commutative factorization. So the authors of this definition, do they prove some theorem out of this, or is purely a definitory type of notion?
It's just a definition.
So they don't get something out of this definition, like, I don't know, we can prove that such and such is true for this.
Well, they have this. They in a sense they prove something like this, except.
Oh yeah, sorry.
Well, this is what we proved, but they basically say the second part, which is that their common core systems work for any quantum state. And so therefore, even if you use a Bell state and you get some locality out, you have a common core. But they don't point out that the first part, that it's really to do with the fact that you're supposing that if you were to make a measurement corresponding to your product measurement, then that's the way in which it happens. It's this kind of weird counterfactual. So.
Thanks.